which are very common also. And these two arrays are Yagi-Uda array and log periodic array. So with this we will come to completion of our course. There is a very interesting story about this Yagi-Uda array. Let me tell you this story first, then we'll see what is this array and the analysis of this array, then we'll go to log periodic array and its analysis. The story goes like this. During the Second World War, when Japan had the upper hand, at that time Singapore was under control of the British Army. So British were occupying Singapore. They had the control of Singapore. Japanese tried to attack Singapore and occupy it. But most of the time Japanese failed because of superior radio physics available with British. They had a very strong radar system. They could detect the Japanese aircrafts and shot them down. It was very difficult for Japan to capture Singapore in the initial stage. But after a long fight, eventually Japan occupied Singapore. When they occupied Singapore, they saw the electronic system in Singapore, electronic military system in Singapore. They started seeing that electronic system, how British were countering the Japanese attack. That was their aim. They wanted to learn, know what was the British system that was countering this Japanese attack. They found that in their radar system there is something written like Yagi, Y-A-G-I, Yagi. They say Yagi, Yagi. In the ships there is Yagi, in the control room there is Yagi. So everywhere there is an antenna, it is Yagi antenna. Then they asked the person in charge of radio electronics, of the British person who was arrested and who was in charge of radio electronics of British Army, what is this Yagi? This person has smiled at Japanese people. Instead of saying what is Yagi, he just smiled. Japanese found that Yagi is a name which is very common in Japan. So they thought, how a Japanese name is available in British Army. So they started probing into it, and ultimately they found that this antenna, the British people were using in the radar, is an antenna which was designed by a Japanese scientist by the name Yagi. So that is the story of Yagi antenna. This antenna was designed by two different Japanese scientists independently. They didn't work in cohesion, or they never worked in collaboration. Both of them proposed this antenna, designed this antenna independently. First Yagi proposed it, followed by him Uda also proposed it. Both of them are Japanese scientists, antenna scientists, and now both are dead. Yagi died about 10 years ago, and Yagi was the last to die. So this is the story. So using the Japanese antenna, the antenna that was designed by a Japanese scientist, British were able to undefeat or Key Party Day, the Japanese force. Japanese didn't know about this antenna. After the war, once they captured Singapore, they could know about the utility of this antenna. So that is how important Yagi-Uda antenna is in those days. Nowadays, of course, we do not. It does not. There are much better antennas, a much better arrays than Yagi-Uda antenna, but it has a historical perspective. Then comes my age. When I was of your age, at that time we used to see TV, and for TV, with the TV set we used to get an antenna. The antenna will be on the rooftop, and a wire will be connected, two wires, two parallel wires, also a cable containing two parallel wires will be connected to the antenna, and it will end in the TV. And the antenna we have to rotate in the direction of the TV station, then we used to receive the signal. So that antenna that we used for TV reception, and that is also the same Yagi-Uda antenna. So Yagi-Uda antenna comes, the importance of Yagi-Uda antenna comes from that. Now to know the Yagi-Uda antenna, the main part of the Yagi-Uda antenna is a folded dipole. So let us look at what is a folded dipole, the basics of a folded dipole. As you know, we discussed about half-wave dipole. A folded dipole is two parallel dipoles. Both of them are half-wave. So two parallel dipoles connected at both ends. That forms a narrow loop. That is what is a folded dipole, which means take a dipole of lambda, then fold it from its center. So you have folded it. That is why we call it fold. So from its two ends will be folded. From the two ends you fold it from its center and stretch it. So it should look like the picture that we are seeing here. So that this manner you fold it. That is what is a folded dipole. Then each arm of the dipole will be lambda by 2. Total length is lambda. Each arm will be lambda by 2. So in effect we can say that each arm is lambda by 2, and the two, we have two lambda by 2 antennas which are connected in parallel. Since two ends are connected, so we will call it the two half-wave antennas are connected in parallel. The D, the distance between the two dipoles, because we are connecting the end points, therefore distance D is very small compared to the length of the antenna. Length of the antenna L is approximately lambda by 2. It should be slightly less than lambda by 2, about 0.48 lambda by 2. So D is much smaller than L. Input impedance will be higher than half-wave dipole antenna. That is the main point. Why we design the folded dipole antenna? Because the input impedance will be higher than the half-wave dipole antenna. For half-wave dipole antenna, we know the input impedance is 73 ohms. When we take a cable with two parallel lines, the cable impedance is about 300 ohms. So there will be a mismatch, 73 ohms, and if you connect it to a cable of two parallel wires, then there will be a mismatch in impedance. So we require this 73 ohms to be very high. Instead of 73 ohms, if we somehow can manage to get around 300 ohms, then there will be matching. Therefore, we require the input impedance of the folded dipole to be higher than the half-wave dipole. That we will see how it will be higher, or why it will be higher, that we will see. There are two methods, we will see both the methods. Then bandwidth also has to be higher than half-wave dipole antenna. If bandwidth is higher, then we can cover a broad spectrum of frequency. That is why we require a higher bandwidth. Okay. Now let us do a simple analysis to see what will be the input impedance of a folded dipole antenna. Now look at a simple dipole antenna which is on the left hand side. If you see the figure on the left hand side, we have a simple half wavelength dipole antenna. Length is lambda by 2. It is fed at the center at the feed location. Suppose the current is I, so ID and D is for dipole, so ID is the dipole current. So at the feed location it is ID. The transmission line which is feeding the dipole, it is carrying a current which is I in, that is the input current. So a transmission line is connected to the feed location. At the feed location we have current ID. On the transmission line that we are trying to feed the dipole, the current is I. Now when we consider a half-wave dipole antenna, simple half-wave dipole antenna, the line current, transmission line current will be same as the dipole current, input current. So input terminal current ID will be same as the current carried by the transmission line. Now what will be the impedance, input impedance at the input point where we are giving the input, or at the feed location? What will the input impedance? Let us say that is Z in and D for dipole. So Z in D is the input impedance. How do you define impedance? Impedance we define as power divided by current square. That is what is impedance. So Z in D is equal to P in, total power input, divided by I square in. Now I square in, I is equal to I in is equal to ID. Therefore P in by I square in is equal to P in by ID square. Now come to the folded dipole. So this is about the dipole. Now come to the folded dipole. When we come to the folded dipole, again we have a line impedance I in. Then we have two dipoles connected in parallel. Since we have two dipoles connected in parallel, the current on each dipole now will be equally divided. Instead of being ID in each arm, it will be ID by 2. So because they are parallel. So two parallel dipoles. Since we have two parallel dipoles, dipole current will get equally divided. Therefore I in will be equal to ID by 2. Because on each arm the current now will be ID by 2. So I in will be equal to ID by 2. If I in is equal to ID by 2, let us use that in calculating the input impedance Z in. So Z in is equal to P in, input power. Power will not change, same power we are giving. Therefore power has not changed. So P in divided by I in square. And now what is I in? I in is equal to ID by 2. So I in square is ID square by 4. So Z in for the folded dipole, so input impedance for the folded dipole is equal to P in divided by ID by 2 square. Or we can say Z in folded dipole is equal to 4 times Z in D. Now 4 times Z in D means Z in D is, we know for dipole antenna, Z in is 73. So Z in FD for folded dipole, it will be 4 into 73. So that will be about 290 or something, which is approximately 300 ohms. So using a folded dipole, we will get an impedance which is about 300 ohms and which is same as or which is very close to the characteristics impedance of a transmission line cable which is a two parallel transmission line. Therefore, the TV cable which has 300 ohms characteristics impedance will be matched to a folded dipole. Now we consider two arms. Now if there are n number of arms instead of one folding, if we have n number of folding, so for n folds we can easily see that the current will be Id by n. Therefore Zin will be n square into Zd. So Zin Nd will be equal to n square into Zd. This is a very simple analysis for the folded dipole. Now let us see a slightly different analysis. This analysis, what it does is, it considers two modes of operation for the folded dipole. One is called the transmission line mode, other is called the antenna mode. In the transmission line mode, the current direction in both the arms are opposite. There will be no contribution to radiation because it is transmission line. Transmission line does not radiate, so there is no contribution to the radiation in the transmission line mode. So this is one. Then in the antenna mode, the current direction in both the arms are same. Because current direction in both the arms are same, then that contributes to radiation. So this is the difference between the two modes. Both these modes will coexist on the antenna. Now consider this. We are connecting the antenna to a transmission line. At the field location, voltage is V. In both the cases, in both the modes, at the field location, voltage is V. Then in the transmission line, this will be Zt for the transmission line mode. So we will call it Zt. The impedance will be Zt. For the antenna mode, the impedance will be Za by 2. Now what happens here? The voltage divided equally on each dipole as V by 2. First, we are going to find out the input impedance. So the first step is voltage is divided equally on each dipole as V by 2. So IT in the transmission line mode, IT is equal to V by 2 divided by
Hello. Sir? Sir, some doubt.
म्यूट करो, आप कथा सुन तो म्यूट करो तमर बहुत हाँ है देखो
ट्रांसमिशन लाइन रेडिएट करिवो माने जतो डिफेक्ट हो ड्यू टू ट्विस्टिंग एंड सम बेंडिंग स्ट्रक्चर ट्रांसमिशन लाइन तो सेड रेडिएट करछि बेरे सर
देयर आर टू वोल्टेज डाइपोल एनालिसिस में इनका मोड दिया जाए पहला ट्रांसमिशन one is transmission line we will consider it as a transmission line that is what is transmission line mode so jota radiate karu nahi jota which has no contribution to radiation then we have a antenna mode which has a contribution to radiation so data को consider करिया पड़ियो जहाँ radiate होची और जहाँ radiate हो data part अच्छे ना तब जहाँ power दौचे all power will not be radiated. Some of the power will be radiated, some will not be radiated. The portion that is not radiated is because of transmission line. We have discussed transmission line and we have seen that transmission line does not radiate. Transmission line, two-wire parallel transmission line will not radiate because current are in opposite direction of the transmission line. So transmission line will not radiate. Contribution due to each line will cancel out. So transmission line does not radiate. So that mode and the radiation mode, both will be considered. So both we are considering here.
Yes, sir.
Paid equally on each dipole as V by 2. Therefore, IT is equal to V by 2 divided by ZT in the transmission line mode. So that is equal to V by 2 ZT. Whereas IA for the antenna mode, it is V by 2 by Z. So that will be V by 2 ZA. So IT is equal to V by 2 ZT. IA is equal to V by 2 ZA. Now total current through a single dipole, since we have two dipoles, parallel dipoles, so through a single dipole, total current I is equal to IA by Z plus IT. Sorry, IA by 2 plus IT. Why IA by 2? In the antenna mode, current is equally divided on both the arms. So IA by 2 plus IT. IT is transmission line mode. That current is constant. So I is equal to IA by 2 plus IT. IA by 2 is equal to V by 4 ZA plus IT is equal to V by 2 ZT. Now take V common. So V into 1 by 4 ZA plus 1 by 2 ZT. Now find out what is the input impedance. Input impedance is equal to V by I. So Zin is equal to V by I is equal to V into 1 plus 1 upon 4 ZA plus 1 upon 2 ZT. So V by I is equal to 4 ZA into ZT divided by 2 ZA plus ZT. That we can write as 4 ZA divided by 2 ZA by ZT plus 1. What we have done is we have divided the numerator and denominator by ZT. So doing that, Zin is equal to 4 ZA divided by 2 ZA by ZT plus 1. So now we know ZT from the transmission line mode. So for transmission line we know this. ZT is equal to J tan beta L by 2. That we know for a section of transmission line, some short-circuited transmission line, for a section of transmission line whose length is L, the impedance is J tan beta L. Here the length is L by 2. Therefore, ZT is equal to J tan beta L by 2. That we can write as J tan beta is equal to 2 pi by lambda. So 2 pi by lambda into L is equal to lambda by 4. L is equal to lambda by 2. So this will be lambda by 2 into 1 by 2, that is lambda by 4. So J tan 2 pi by lambda into lambda by 4. Lambda cancels out. 2 in the numerator cancels 4, leaving 4 in the denominator, leaving 2 in the denominator. So ZT is equal to J tan pi by 2. J tan pi by 2 is equal to infinity. As you know, tan pi by 2 is equal to infinity. So ZT is equal to infinity. So for Zin, if we put Zin is equal to 4 ZA by 2 ZA by ZT plus 1. For ZT, if we put infinity, 2 ZA by ZT will be 0. Therefore, Zin will be ultimately 4 ZA, because it will be 4 ZA by 0 plus 4 ZA by 1, that is 4 ZA. So Zin is equal to 4 ZA. ZA is the antenna impedance. So antenna impedance is equal to, whatever was antenna impedance was 73.3. So 4 into 73.3. So 4 is 2 square. So Zin is equal to 2 square ZA. This is the exactly same result that we have found out in the previous analysis. For n-fold, we can easily show in following the same method. It can be similarly show that Zin is equal to n square into Zin. So this is how we find out the input impedance of a folded dipole antenna. If you want physical insight, you follow the second method. If you want to do it easily without physical insight, you can follow the first method. Both the methods are correct, and in both the methods, if you follow either of the method, you will get full mark. Okay. Now we will come to Yagi-Uda antenna, the construction of an Yagi-Uda antenna. The Yagi-Uda antenna, it is an array of active and passive or parasitic collinear dipoles. What does that mean? Collinear dipole elements with a folded dipole as the active element. Active element is the element which is directly fed, to which you give the feed. So power is fed to an element. If power is fed to one element or power is collected from one element, then that element is called the active element. Other elements to which we do not feed directly, the power is not fed directly from a source, those elements are called passive elements. The Yagi-Uda antenna contains both passive element or parasitic elements as well as active element. The active element is a folded dipole. These elements are arranged collinearly, which means they are on the same axis. Now you can see in the figure, the elements are across the z-axis. So they are centers. Center point of each element is on the z-axis. Therefore, they are collinear dipole elements. The active element is directly connected to the feed. Passive or parasitic elements are electromagnetically coupled to the active element, but they are not directly connected to the feed. Feed is connected to the source. Usually feed is connected to the source or to the receiver. So this is the construction of the Yagi-Uda antenna. Now we will see what are these passive elements. One of the passive elements is slightly larger than the active element. Only one passive element is slightly larger than the passive element. So this is called the reflector. The size of the reflector is about 5% more than the driven element or the active element. The driven element or the active element is half wavelength. Length of the active element or driven element is half wavelength. The length of the reflector is greater than half wavelength because it is greater than the driven element. Since it is more than length is greater than half wavelength, therefore it will be inductive in nature. So the reflector is inductive. Since it is inductive, it will induce a current lag. So it induces current, and because of the currents, there will be a voltage lag. It reflects the electromagnetic field that you can see here. The leftmost picture shows a driven element, pure driven element. It is a dipole antenna. Therefore, the radiation pattern is rotated figure of 8. Now, when we bring a reflector close to the driven element, the field on the left side of the driven element will be reflected back towards the driven element. Therefore, you can see the field pattern will slightly change. It will be more towards right side. Towards left side, there will be a small amount of power will go towards the left side. Most of the power will be concentrated towards the right side. That I am showing here. Distance between these two elements, the driven element and reflector element, is about 0.04 lambda. The reflector length when you design an antenna, particularly for TV antenna, if you are designing it, the reflector length is equal to 492 divided by frequency given in megahertz. So 492 divided by frequency in megahertz. This is the reflector length in feet. The driver length or the driven element length is equal to 478 by frequency in megahertz in feet. So both these are the two formulas that we usually use when we design a TV antenna. Then we look at the other elements. These are called the director. So one element is the reflector, other elements are the directors. The length of the directors is about 5% less than the driven element or the driver. The driven element is half wavelength. Since these lengths are smaller than half wavelength, they will be capacitive. So their impedance will be capacitive. Since their impedance is capacitive, here the currents will lead the induced voltage. In the previous case, in the reflector case, current lags the reflector voltage. Current lags means phase of the current lags the reflector voltage. On the induced voltage, here the current phase is more than the induced voltage. Since the current leads the induced voltage, therefore it adds additional energy to the signal. So it will be more directed, it will give a directivity. That is because of conservation of energy, we cannot have additional energy. Additional energy cannot be created. But because of leading current, it is going to add additional energy. So from where it will get the energy? It will get the energy that got reflected, and that energy will be concentrated in a particular direction. Since it will be directed, it will be concentrated in a direction, so it will be more directive. So it will be directive, and along that direction the energy will be concentrated. So that is what we call adds additional energy, and since it becomes directive, we call it a director. So the director, the job of the directors is to direct the beam or make the beam more directive. Separation here between the beam element and the director, or between each director, the separation is about 0.04 lambda. Now remember another thing, the directors can be of same length, or the director lengths will gradually decrease. So the largest length will be nearer to the driven element, smallest length will be the farthest element. So they can be of same length or they can decrease. There is no problem in either case. If they decrease, it will be slightly more directive, that much. So when you point this antenna towards the TV station, the director should be towards the TV station. Reflector should be in the opposite direction of the TV station. So the power comes from the TV station, it gets reflected by the reflector, and it gets directed by the director towards the TV station. Now the length of the director is 461.5 by frequency in megahertz. Now what is meant by frequencies in megahertz? F is equal to 360 megahertz. Suppose F is equal to 360 megahertz. So it will be 461.5 by 360, not 360 into 10 to the power 6. As you know, 1 megahertz is equal to 10 to the power 6 hertz. So 10 to the power 6 will not come here. It will be only 360. So director length is 461.5 by frequency given in megahertz. That much of it. Now let us consider the operation. The reflectors adopt the fields of the driven elements in the direction from the reflector towards the driven element. Additional gain is achieved by using additional directors in the beam direction. So you keep on adding these directors, will keep on increasing the gain, but we cannot go on adding infinitely many directors because that is not going to add gain. After a certain point, the increase in gain is very less, so it is negligible. So by adding, we will get some gain, additional gain, but we cannot keep on adding hundreds of directors. 5 or 10, somewhere there, that many directors we usually use. It provides a gain of the order of 8 decibel, and front to back ratio is 20 decibel. Front to back ratio means the power in the front beam divided by power in the back beam. As I have shown you, there are two beams. One beam is towards right, one beam is towards left. The beam towards left is smaller and the beam towards right is larger. So the power is more on the towards right, that is the front beam. The beam towards the left is smaller, that is the back beam. So the power ratio of those power is 20 dB. Now we have seen the input impedance. Now let us do a complete analysis of impedance for the reflector antenna. When we have reflector, we have two antennas. One is the reflector, other is the driven element. So there are two elements. If there are two elements, both are carrying currents. So remember that if there are two current carrying elements which are close to each other, then they will induce current on each other. So element 1 will induce current on element 2, element 2 will induce current on element 1. There will be mutual coupling between them. So therefore, in this case, Vd, or the voltage on the dipole, is equal to Id into Z11, which is Id is the current on the dipole driven element, into Z11 is the self impedance of the driven element, plus IR is the current on the reflector, into Z12, which is Z12 is the mutual impedance seen at the input point due to the reflector. So that is Z12. So Vd is equal to Id Z11, this is for the driven element, plus IR Z12, this is for the reflector element. Similarly, we can say VR. VR, you can see that the second element which is carrying current IR, there is no voltage, there is no source. So voltage is 0. So VR is equal to 0, but that we can write as Id into Z21. Id is the current say on the first element, Z21 is the input impedance or due to mutual coupling. So Z21, Id into Z21 plus IR into Z22, that is the self impedance for the reflector. So IR is the current on the reflector, Z22 is the input impedance of the reflector. So Id into Z21 plus IR into Z2. So from this we can find out what is IR. IR is equal to minus Id into Z12 by Z22. Now put IR in Vd. So Vd is equal to Id, take Id common. So Vd is equal to Id into Z11 minus Z12 square divided by Z22. Now what will be Zd? And Zd is the impedance of the dipole. So Zd is equal to Vd by Id. We can easily find out what is Vd by Id. So Vd by Id is Z11 minus Z12 square by Z2. Now what is Id? We have to find out what will be Id. Id you can easily find out now. Id is equal to Vd and divided by Z11 minus Z12 square by Z2. Now what will be IR? IR will be minus Id into Z12 by Z22 ID we have found out. So this will be minus Vd by Z11 minus Z12 square by Z22 into Z12 by Z22. So that you can write as Vd into Z12 divided by Z12 square minus Z11 into Z22. This is very simple, just simply algebraic manipulation. So accordingly we can find out what is Zr. We have found out what is Zd. Now we can find out what is Zr. Zr is equal to Vd by Ir, that we can find out easily. Vd by Ir is equal to Z12 square minus Z11 into Z2 whole divided by Z12. So that is Zr. So this is the impedance analysis. Similar analysis can be done for reflector, but that is not done for directors. That is not necessary. Once you do one analysis, this is similarly other analysis others can be done. We need not do that. This is enough. Then what are the advantages and disadvantages? Advantage is it has high gain, it has high directivity, it is a broadband antenna, it consumes less power, it wastes less power, most of the power is radiated. It has a balanced impedance point. We do not require a balloon at the antenna. Input impedance is 300 ohms, therefore it can be directly connected to a cable, flat cable. It can be directly connected to a two-wire flat cable. Disadvantage is it is affected by noise and it is affected by atmospheric effects. These are the two major disadvantages of the Yagi antenna. Then the applications are mostly TV reception antenna, usually single frequency use. Then we can use super gain antennas by stacking many Yagis. That you can see there are two Yagis here. In this picture we have two Yagis, that is called a super gain antenna. So gain will be much more than a single antenna. So we can have super gain antennas by stacking many Yagi antennas. With this we come to the end of Yagi antenna. We will consider the log periodic antenna after a break. Let us take a break here for 10 minutes. Then we will come back and study the log periodic antenna.